Very well. Now, Ruth was talking about surveys with equal coverage. So we try to, the design of those surveys implies that we try as much as possible to cover the study area with the same probability for each of the points. But sometimes that's not possible. Sometimes we just have data, for instance, from surveys we do for photo ID work, where we don't cover the area in a systematic way and with the same coverage probability. And so, in that case, we have each of the points in the study area have different probabilities of being sampled. Ones will be sampled more, others will be sampled less. And this, we have a case. Here in Madeira, we have this overall as a study area, for instance, we can consider, and we have a grid. But actually, we have some of the data we collected didn't cover the whole area, but just covered here. And you can see these bits are not so much not covered at all. This less, and this a lot, this area. So it's kind of a shame to lose this data, to lose all this effort to try not somehow to model that and be able to incorporate this kind of data for abundance estimates and for distribution. So there are new ways of dealing with this, which have to do with spatial modeling. Okay, here is just a show two examples of equal coverage surveys we did in the past, and Ruth already showed. Here in Madeira between 2001 and 12. And this is by helicopter from 2002 to 8, and we did cover all these areas, these more offshore waters and these more inshore waters. And then we can actually use to model all of these, the ones with equal coverage and the ones with unequal coverage, and we can also model all of those in a more complete approach, which will also use spatial modeling. Again, as for equal coverage surveys, for an equal coverage survey, so the photo ID work or even data we might get from whale watching boats, although here is more complicated, more tricky, and I will not talk about this here, but we can talk later if you guys want. What you really need to do is to actually get angles and distances, the same way Ruth talked about, to the sightings under the same assumptions. That is, accuracy, the angle and distance has to be taken when the sighting is first spotted because of the response, and with accuracy using either you can do it visually, but then the accuracy is not the same, and you should use angle boards also to measure the angles. And with this, what you will have is also a detection function you can have for that boat, and from that at the platform at a constant height. So I forgot to mention before, the sightings have to be done from a platform which is always the same, because the distance you can see and what you can cover, and if you measure with the binoculars, the perception of the horizon will change with the height in the boat. If you're close to the water, the horizon will be probably at 3 nautical miles. If you are 4 meters above, it will be probably 15 nautical miles. So you still have the same general perception of the horizon, but actually the distances you are covering are completely different. So it's really important to have a measure of the height of the platform and the observer. So what we do for each observer, we measure the height of the platform and then the distance to the eye, so we can have a precise height of each observer, which we'll take in consideration. And again, you get a detection curve. And this detection curve, as explained before, will explain how the detection probability of a particular species will change with distance, with the perpendicular distance from the transect line for that particular boat. So each boat has to have its detection curve for the study period under these very kind of strict conditions. However, you can do a lot of things with that, so it's worth the effort. In this case, afterwards, what you do, and I will explain, I will show the results later. You get a transect line, and you segmented that in small segments, which will be called, or are sampling units. and they are smaller or bigger according to the resolution you want. So in this case in Madeira we used grid cells of 2 nautical miles, 4 by 4 kilometers. So when we then later generate a map or we calculate abundances, we calculate for cells of 4 by 4 kilometers using models. So we get the transect, we associate the sightings, we take the bits where we are not in effort. That's another issue which is really important, is a measure of effort. And the effort here is when are people under those conditions searching? Because if we just use a transect from the GPS and we don't have anyone looking, then we will be passing by animals which will not be accounted for. And so we will have an estimate which is absolutely wrong. So you need to know when we have observers looking at those conditions and searching. It doesn't mean you don't have to do it all the time, but if you do like for 2 hours, you just stick to that and you take starting effort and effort. And then you can use the data on those 2 hours to actually use in this kind of approach. And here we're talking about the application generalized additive models. It is important that these transects used in the study area cover the range of the covariates being used. So let me try to explain what I mean here. Rather than using just the coverage, the equal coverage, what we do is we use covariates like depth, distance from coast, temperature of the water we get from satellites for the whole study area. And then we use that, the relationship between the presence of the animals and those covariates, to extrapolate from our transect lines to the whole study area. Okay? So, but what we need, what is one of the important assumptions, is that we cover the range of those covariates. For instance, if we're using a study area, like here, we cover the water from zero, the depth, from 0 to 3,000 meters. So we should sample, even if it's not equally in the area, the range of the covariate depth from 0 to 3,000. Because if we don't go to 3,000 meters, we don't have any information on the presence or absence of the animals at that depth. So that the same applies to temperature. So if we have on the study area temperatures that go from 20 to 22 degrees, we should, as much as possible, be able to cover the range of those temperatures. And this applies to all covariates that we use as much as it's possible. In reality, we sometimes can't do that, and the model sometimes let us get away with it, and sometimes it doesn't. And if it doesn't, we get in trouble and we don't get any proper results. So it is important to think through this and try to get that kind of coverage. In this case, although we had more effort here, a low depth, we still had effort that covered the whole range of the covariate depth. So we have information out there from that, the range of that covariate, and then we can apply that into the model. And so this is what we did, and we're doing now for, in this case it's a model for Rudous whales. And here, I'm sorry, and I'm not seeing well, I forgot my glasses somewhere. We're using area of escarpment, areas with slope. We're using slope, the minimum value of slope, and longitude. This is the final model we got to actually model the distribution of Rudous whales in our waters. And what we have here is, although we have far more effort in this area, which is because of the photo ID data, whale watching observers data and all that, the model still takes that into account and compensates for the areas with less effort, exactly using the covariates to explain how that variability changes. So we can use lat longs, depth, sea surface temperature, chlorophyll A, primary productivity, distance from coast, and any other models, as long as we have information for the whole study area. And I go back to each one of these cells, we have to have information as much. We can miss one or the other, a few, but we can't miss all of them. or most of them. Okay? And from here we can model distribution, and if we have the detection function that we obtain from distance sampling, we can estimate abundances. Okay? And usually what we do is we tend, when we want to get robust abundance, we use the systematic surveys. We get abundance from there, from distance sampling, and then we model. Usually the covariates explain some of the variability in the data, and we can get better confidence CVs, confidence intervals, and better, so more precise estimates. And then we can confirm one against the other and see if the estimates we're getting are reasonable and consistent. Nevertheless, if you don't have that, like systematic surveys, but you do collect data on distance, effort, the covariates, detection covariates, as Ruth told about, which were related, like sea states, anything that might affect detection, we can model that, put that into the models. And the environmental covariates, then we can estimate abundances and also have distribution maps. There is another catch: you need a minimum number of sightings. And usually these kind of models are data hungry, so they demand a bit of data. So we tend to use several years. In our case, this study we're doing is 20 years of data. We're talking about 60,000 kilometers of effort using different platforms to be able to get a robust approach.
Just a quick question.
Yes, no problem.
Because you said you extrapolate using these covariates to all around the island. How do you see which covariates actually are representative?
So that's actually what we do in the model. That's the model will tell us statistically.
Okay.
If the relationship between the covariate values and distribution of the sightings over the range of the covariates, if they are significant or not.
Okay.
So it's the model actually tell us what we can retain in the model or what we should throw away because there is no relationship. I don't have here, but some of most of them, we're using like 43 covariates. Most of them it's like a flat line, which means there's, over the range of the covariate, there is no change in the response, which means that the way that the data is distributed is not related with that covariate. But in this case, you can see, as the area of the escarpment increases, the expected number of sightings will increase. Okay? And this case here is not the number, exactly it's the log, because it uses transformations to transform data which is not linear into linear values. And for instance here, there is a decrease, although the value is a small effect, but there is a decrease with years. So we should kind of expecting less detections with years of British waves from 2005 to 2015. But then, do you see this gray area? That's the uncertainty. So you can't say much because the uncertainty is also big. In that case, you can tell because the uncertainty around the line is smaller. So the uncertainty goes with it. Here, if I put the line in any of those points, it will still be within the limits of the uncertainty, so you can't tell much. There's an effect, you take it into the model, but you can't read that as something which is actually happening. In this case, there's a clear influence, because the uncertainty around it is smaller, and it goes together with the line. The uncertainty also increases not increases. The uncertainty maintains as the value increases, so we know that that's happening. Okay? That's how we do it. Okay, now, any questions on this? Any further questions? Then I can...
Yes.
Yeah.
Maybe I missed part of what you just said on this slide. So the color, color map?
Yes. So this is, here we are not using absolute abundance because I'm not using the detection function values. I'm just using relative abundance. So blue tells there is no presence, and this light color, yellow light, it tells there's within this limits of no sightings and the most sightings where we expect more sightings, the highest presence of the animals. We can't measure it in terms of densities, which are numbers of animals per kilometer. because I'm not using, in this case, the detection function. I'm just using effort and sightings. But so it's kind of a relative measure, which doesn't translate the number of animals. So it just tell you that there's, on average, more animals here during these 20 years than there were here or here even. So it tells us the areas they were more present, on average, during this time period.
And the black dots?
Are the sightings. And then you can ask, well, but here you have far less sightings than here. But truth is that if I go back, that this is the data I use of effort, I have far more effort here than I have here. So the model takes that into consideration.
And then the uncertainty also.
Also the uncertainty will come around that. Okay, so that's how it deals with it. And actually, these dots are from bottlenose dolphins. So there's no relation with the other one. Yes?
So just to interpret a little bit, because around, taking for example, Porto Santo,
yes,
you have a more, I don't know if the term is the homogeneous dispersion of sightings.
Yes.
Because, why? Because the sightings that have been done there were by not using opportunistic platforms?
No. In this case, nothing to do with that. It has to do with the covariates again. And if you look, let's use just this covariate because, well, this or even this one, because they have higher values. So it means that on the range of the area of escarpment here, let me see. This is an area of lots of slope, and the area there is quite big. So, and we have a strong relationship there, which will reflect here. We don't have so much sightings, but what we're using is how the sightings are seen in the range of that covariate. So it tells us that on average we would expect, or we expect more sightings there, even if we didn't see it, because we found that relationship. Okay? It doesn't have so much to do with having systematic or non-systematic. It's just the way you apply the data, the methodologies, and how we use it in analysis. If it's consistent, then it is proved to be reasonable to accept this. Okay? But for instance, if there is a bit here, which we didn't survey, so if we got a high density area there, it would be what we call an extrapolation, because we don't have any data to validate that. So it would be, and we can also do that. For instance, I could apply this model to an offshore bank and say, according to these covariates for this species, we would expect this distribution there. And then we could go and have a mission to that offshore bank and confirm that, or say no. There are other covariates which are affecting the way the animals are using this area. Okay? So that's how it works. You usually tend to use your data to infer on the area. So use part of the area covered, then you infer for the whole area, but you still have to have effort covering the whole area, even if it's not evenly distributed. Did you understand? So, but again, we can have then models for different species. Some species where very few sightings for each of the surveys. But if we combine them all together, then we can get enough sightings and enough effort to be able to model. And then we have distributions for that species. What I have to say is this is an average distribution for the period of the last 20 years. So on average, we would expect this. Then if you go at a particular time, it doesn't mean it will be like this. The probability of being like this is higher than others. So it will be higher, you'll have higher probability of finding animals here that you will have than having there.
How big does the data set have to be on the number of animals?
It will depend. We can. I'm trying now, and I'm getting some models. I'm getting away with 15 sightings, although not very confident on that. But I would say 30, above 30, you need that. You need that. But then you need also other conditions, because then you can have a model, you can have a map, but you don't know what it means. Okay? Because you don't have all those conditions in terms of coverage of the covariates and all of that. And if you want to have absolute abundances, you need the detection curves, for sure. Otherwise you can't estimate the width of the transect that you've done, and from there the number of animals, density of animals you would expect in that transect that you have done.
This is more for stationary animals, species, or not?
No, this is actually for mobile species like cetaceans. What you do need to do, it's really important, is you take the distance to the point that you see it.
Yeah.
The thing is, even if they are mobile, if on average you have a high probability of seeing them there, then there will be more time there. Otherwise there would not be a higher probability of seeing them there, isn't it? So that's what you do. It doesn't mean that you might get there one day, and happen to us several times, when we're trying to tag animals, and they are not there. They are elsewhere. But on average, we'll have a higher probability of finding them there than here. And actually we went out, and I will show you, this can be a good way of going to satellite.
I think effort will change those numbers.
Hmm?
Effort can change those numbers.
No, but the effort, it is important, it is crucial. Without effort you can't model. The only thing these models do is actually being able to integrate in the same final result different approaches with different efforts and balancing that using the covariates as the way to explain how the variability is on your study area. So we get kind of the same results. I did modeling from 2007 to 12 for these species just using systematic surveys. And the good thing, I'm happy, not for all the species, but some of the species, the same patterns, they change a bit, but they are there. The high density areas, they are the same. So it means they not only did not change over time, so they kind of, the whole 20 years period is similar to that, but using different data in there, you will still get the same pattern.
It's funny.
It's guys, sometimes it's hard to believe.
The area with more effort
Yes.
has the better probability, right?
No, that's why you need to compensate.
That's why I
Because you
where
can-
I want to go.
No, but you need to compensate, that's why...
Bigger probability and
No.
more sightings.
Now the thing is, I will go
Unless
back.
the spot
Now,
about
if you can see this,
which is, well...
I can have, I can go here all the time, and if the animals are not there, I can have 99% of the effort here, and the animals are not there. The probability of detecting them is 0. Period.
I believe, but in
So-
zoos, I've never seen this modeling for these zoos.
But there is.
But, yeah, I'm sure there is. But when we don't have animals on one area or there's too many boats, if we start battling in another area, the animals are there too. It's a question
No,
of effort.
that's why I see.
I'm sure if you go to the east side of
That's why I say,
where
on
there's
average,
food there, for sure there's
No.
animals there.
I will show on average, and I'm talking about, you have to think this in terms of average, and then with each average, because this is sampling, you have uncertainty, a level of uncertainty. That level of uncertainty can be big or can be small. Some species you have really high, and you can say, I am absolutely sure, or not absolutely sure, but I am confident with a high degree that this model is correct and will represent the general distribution. Sometimes you will also say that I don't have that uncertainty, so they can be spread around. And there are two reasons for that. One, because the animals are really spread around, or two, because the data we have doesn't allow it to have a more precise result. For instance, pilot whales just consistently give us here, in all the models we have, as the high density area. And we are highly certain of that. Because why? Most of the time they are there, and they are not elsewhere. We have sightings elsewhere, but it's not the same way. And I'm going to show you, regarding this, the model, some of the effort we did before, next, so that you can understand.